Have you ever considered how big breakthroughs in science, engineering, and medicine occur? The popular misconception of how a breakthrough happens is perhaps a eureka moment while working on a project, and in that instant, the next big thing is born. Although that may happen sometimes, the truth is that most big breakthroughs are not eureka moments at all, but actually take years of painstaking work, trial and error, and rigorous testing before the finished product is ever realized. Researchers in the world of engineering and science almost always move in small, incremental steps, slowly building the case for these new revelations until they are sure the research is ready to be shared with the world. Then, and only then, is when we in the general public hear about it. Although it may not be quite analogous, just think about the moon landing as an example of this phenomenon. Most of us are familiar with Neil Armstrong's famous words when he first stepped onto the moon.
It's one small step for man, one giant leap for mankind.
For those watching it, that moment may forever be viewed as perhaps the most tremendous scientific and engineering breakthrough in the history of the world. Clearly, that event was enormously important for many reasons, but that first step on the moon was actually the culmination of millions of smaller incremental steps from tens of thousands of others that allowed it to take place. This basic idea is true for all scientific study. Researchers and engineers generally take an idea and meticulously study it to make sure that all bases are covered before new technology reaches the general public. NASA's Environmentally Responsible Aviation Project team members are following that same philosophy as well. This team has been working for years to find ways to reduce aircraft drag, aircraft weight, fuel consumption, engine emissions, and aircraft noise. In order to achieve these lofty goals, the team did, in fact, take incremental steps to make sure each project was viable. Now, toward the end of the ERA project, the team is ready to take the lessons learned from the smaller tests and begin putting all the pieces together, preparing to show the world the next big thing in aeronautics. NASA X has been at the forefront of the ERA program since its inception. This 6-year endeavor has progressed from innovative ideas to multiple designs, wind tunnel tests, and actual flight hardware. And the aerospace industry has taken notice that these technologies are ready to dramatically improve aircraft efficiency. Part 1 of this episode of NASA X looks back at some of ERA's earlier tests to see how those early successes and failures paved the way to the larger, more advanced tests of today. And we will see what the future holds for many of the ideas and technologies that have been developed by some of NASA's best and brightest engineers and researchers. When the Environmentally Responsible Aviation Project was first implemented, it was clear the stated goals would be hard to reach. The team was tasked to reduce aircraft drag by 8%, reduce aircraft weight by 10%, reduce fuel consumption by 15%, reduce emissions by 75%, and reduce overall aircraft noise by 75%, all by the year 2025. Compounding the difficulty of making such dramatic improvements was the fact that many in the aviation industry believed that the modern tube and wing-shaped aircraft had reached its maximum ceiling on efficiency. When NASA first undertook this challenge, they realized they would have to bring an A-team of NASA engineers from numerous NASA field centers, along with highly skilled teams from industry and academia in an effort to find these new efficiencies.
We've got new airframes, 8 different technologies that we've worked in Phase 2, a myriad of 60-something technologies we worked in Phase 1 and we looked at. And we will be delivering at the end of this year technologies that say we can meet all of those goals. So it is an unmitigated success, and every one of our partners in this is getting something out of it.
Some of the major areas of study for the team included looking at engine redesigns, airframe redesigns, materials testing, and even developing new aircraft that integrate the wings into the aircraft body to increase efficiency. This unique design is called the HWB, or Hybrid Wing Body Aircraft. The HWB began its life as a series of computer models and then was upgraded to sophisticated wind tunnel models. Once the team was satisfied the HWB concept showed significant promise, it was upgraded to a flying scale model aircraft. 122 times the hybrid wing body models flew over the dry lake bed in California, where so many previous X-planes had flown before. And with each flight, the engineering data helped validate this unique type of aircraft design. Researchers feel confident that the strides they have made in this aircraft design will pay huge dividends in the future. Just watching footage of early aircraft shows how far we've come in only 100 years. As an example, most early planes were made out of wood and canvas, but as planes became more powerful and efficient, materials began to change. Today, we're aware that most planes are made out of lightweight aluminum skins, but the industry is moving toward the use of composite materials now as well. In fact, the Boeing 787 was the first all-composite airplane ever produced, and it took its first commercial flight on October 6, 2011. Although this plane is state-of-the-art, NASA's ERA planners believe that they can improve the strength of composites while making them safer as well. The idea they're investigating is called PRSEUS, or Pultruded Rod Stitched Efficient Unitized Structure. Early testing began with small pieces called coupons. They were developed to a point where researchers believed they could be tested on a larger scale. NASA's team built larger test sections and eventually brought them to this lab for stress testing. With this test, designed to bring the article to failure mode, the team applied pressure until the piece snapped. The data was used to further validate PRSEUS, and now the team has decided to build and break a nearly full-scale piece of PRSEUS material.
NASA and Boeing have been working together for quite a few years developing lightweight structure for commercial transport aircraft. What we're seeing today is the final piece of a project called Damage Arresting Composites, where we're trying to develop a new structural concept that will be applicable to lightweight structures for commercial airplanes. And what you see here is a 30-foot-long test article that we'll be testing at the NASA Langley Research Center by applying the kinds of loading that it would feel if it were in a real airplane.
But with a piece this large, a major hurdle lay in front of them: how to get the piece from California to Virginia for testing. Traditional methods like trucking and train travel would not work due to bridges, overpasses, and some road weight restrictions. The solution was to fly it across country, but no ordinary aircraft would do. Ultimately, the team enlisted the service of NASA Johnson's Super Guppy aircraft for transport across country. This Cold War-era aircraft was specially designed with a hinged front-loading system that could just barely accommodate NASA's cargo. It was not lost on team members that this old and slow beast of an aircraft was transporting a test article that will undoubtedly be used in many aircraft of the future. On a cold December night, The aircraft landed in Virginia for an early morning offload. Here is Dr. Fay Collier to explain what is next for this test.
Today we're here at Langley Field unloading the PRSEUS multi-bay Colts multi-bay box that will be tested in the Colts facility. So we've been working on PRSEUS for about 10 years now, partnered with the Air Force, partnered with Boeing, R&T. And we started off with small coupon testing to prove out the concept. We built a small box that we tested three years ago to prove that the concept could take pressure and would meet the design constraints. We went from there to assembling this piece of 30-foot structure that we're going to test in the Langley Combined Loads Test System down the street here. So a long effort that has gone into this with NASA and Boeing, culminating in the delivery of this 10,000-pound piece of aircraft structure. We'll stick it into the facility, we'll mount it, it'll be eventually pressurized to various pressure readings. The idea is to twist and turn the part to see if it'll sustain the design loads that would be needed if we were to build a real airplane out of this.
This facility will prove to be a valuable tool for researchers. These types of tests will help in investigating damage tolerance and any repair techniques that may be applicable. One of the key test points that will be addressed in this round of testing will see how PRSEUS handles routine damage that might be expected, such as a technician dropping a hammer. Researchers need to understand how this new material will react if minor damage occurs. To do this, a unique test rig has been designed by hand. Here is Andrew Lovejoy to explain.
So some of the things that could impact the plane are rocks or debris that's on the runway when it's taking off or landing. As I said, you could have mechanics that could hit it with a tool, or a vehicle driving by could hit it. And all those types of things can cause damage. And on the exterior, you're more likely to have a higher energy because a vehicle hitting it or something being thrown up by the tire is going to be a much higher velocity than, say, a tool drop. So barely visible impact, if you're doing walk-around inspection, it's a damage that you would barely be able to see. So if you're at that level, the aircraft has to be able to sustain the loads that it would normally see, even with that damage in place. So you have to be able to analyze and then test to make sure that you can hold those loads. So what you have to do is an impact test. So we're doing an impact test, and if you were going to impact at the top on something, you would just have a free-falling, you could have a free-falling weight that would come down and hit. And that's fairly straightforward because you have a mass and you have a height, so you can have a straightforward calculation of the energy. If you wanted to hit on the side, we have spring-loaded, but for the multi-bay box, one of the things we're doing is hitting on the keel, which is the bottom. So we have to have an impact that's going upwards. There's very limited space in Colts. You can have an air-driven projectile, you could have a spring-loaded, but those to me are less controllable. So instead came up with the roller coaster impactor. So it's really a controlled drop. It comes down the track and then it'll go back up, and when it hits, it's going in a vertical direction. So in order to impact on the keel, we needed the impact weight to go up, and we didn't have any device to be able to do that. So from scratch, we designed and built the roller coaster impactor. The second main part is the track itself. The track itself is to control it and make it go where we want it to go. When it's rolling down, gravity's keeping it on the track. When it starts to go vertical, it wants to flop. So there's actually two pieces of track that will encapsulate this right before impact to guarantee that we're getting that vertical impact on the bottom of the keel.
Numerous tests were performed in the Colts facility to check the box's ability to meet what engineers call the design limit load and the design ultimate load. In aerospace engineering, the term design limit load refers to the maximum load factor authorized in flight. It is extremely unlikely that an aircraft will ever reach this limit during its lifetime. The design ultimate load goes beyond that and is the amount of load applied which will make the component fail. In this case, the ultimate load factor is 1.5 times more than the limit load. With testing and data acquisition complete, researchers found the PRSEUS box performed beautifully under extremely stressful conditions. It actually performed above the expected design ultimate load factor, which means the box is even stronger than predicted. With that type of result, researchers feel there is an opportunity to lighten the box even more, potentially making future aircraft even more efficient. Although this stage of the testing is complete, the team has reams of data to look over and will continue working to make the aircraft of tomorrow stronger and more efficient than ever. The hinged wing design on aircraft has been around since the early 1900s. Currently, this design is state-of-the-art and almost magical in its operation, extending and retracting during takeoff and landing. But hinged flaps have drawbacks, such as high noise levels, and their design affects the flow over the wing, making them less efficient. NASA is currently working on improving specific aspects of wing design and has partnered with a small company out of Ann Arbor, Michigan called PRSEUS to combat these problems. Their innovative design has the potential to revolutionize flight by having the wings on aircraft act more like a bird's wing, rather than the traditional flap system we have now. Here is Dr. Sridhar Kota, the inventor of the Flexus wing, to explain.
So with the current flaps, once they're tucked in, you don't want to move those flaps because the flow will separate. So the aerospace community has known for a long time that if you have a seamless wing that can be morphed in flight to maximize the performance, then you can get significant fuel efficiency. And actually, Wright brothers did that for roll control.
The idea to have aircraft wings morph is not a new idea. In fact, the Wright brothers' first designs used morphing wings to help with controlling flight. But as aircraft became heavier and began using stronger materials, aircraft designers were forced to stop using the morphing wing technique and use flaps and slats, which have been in use ever since. Designers have long known that reducing the use of flaps and going back to a morphing wing would be more efficient, but until now, no one was quite sure how to make it happen. While looking at this problem in the early 90s, Dr. Kota came up with an idea called compliant design that uses techniques that are borrowed more from nature than from traditional mechanical designs.
Everything we engineered, if you look around the objects around you, anything that is strong is also very rigid. And when you want mechanical functionality in the design, you put multiple parts, springs, cams, gears, and make intricate mechanism that works beautifully. Whereas designs in nature are different. They are strong, but they are compliant. They're flexible. So you can see the trees bending in heavy winds, so they bend rather than break. And you can see countless examples in nature where you get pretty intricate mechanical motion without conventional joints. And in fact, 80% of living creatures are invertebrates, and they do pretty well with the locomotion and other mechanical functionality without multiple joints and links. So the question is, how do we capture that, where we want a monolithic structure that can do mechanical motions without joints? So the idea is that how do we get this compliance, the flexibility distributed throughout the structure, and how do you design structures like that? So I'll give you a simple example of what I call the distributed compliance. And you can see this here. So here, this can be a monolithic design, no joints. And when I apply force on these tabs, and you can see it move, so you can get large deformation. But the way it's designed is you have very small stress in the structure, which means every section of the material shares the functionality, shares the load, so the stresses are evenly distributed. that's how we have very small stress, very small strain. It works in a linear elastic strain region, so you get large deformation, and which means you can do this multiple times. You can do this millions of cycles and still not fail.
Although the exact technique is still a trade secret, the PRSEUS team's design uses a proprietary algorithm in a way that minimizes the force it takes to morph the wing to a prescribed shape. This technique also has inherent mechanical advantages in that it is very stiff to external loads. Simply put, the design is incredibly strong, but does not need huge motors to morph the wing. To test this concept further, NASA's ERA team decided to place a PRSEUS wing on board an aircraft to test in flight. The team removed the traditional flaps from a Gulfstream aircraft and replaced them with a PRSEUS wing for the initial testing. Tom Rigney of NASA Armstrong explains.
The reason it's important is because one of the contributors of noise, one of the largest contributors of noise for an aircraft, when it comes down to approach for landing or for takeoff, there's a lot of noise that's generated by the spaces and gaps from existing flaps that are on an aircraft. And so what this does is it reduces that noise by eliminating those gaps. And they have a smooth, continuous surface rather than having gaps. And it can reduce sound within up to 4 to 6 decibels, which is significant. This technology is really helping aviation, the whole aviation industry. It's something similar to what we had with winglets. So winglets came on aircraft and made them much lighter and more efficient and more effective. And this is similar to winglets. We're going to be able to take an airplane and have wings act more like a bird. Instead of having just these boards that come down and all locked in place, we're going to actually have morphing and shaping wings just like a bird would do. And that makes the aircraft more effective in terms of flying, in terms of efficiency, fuel savings, and it's going to save hundreds of millions of dollars for the public for flying. It's also going to make planes lighter weight, which allow for more luggage and other things to go on board. And it's more of a green type of technology, less carbon in the air for the world to have to deal with later. So this is going to be really helping out the environment as well as saving money. So it's really a great technology.
The first tests of this design were very successful and met all of the stringent stretch goals that engineers set out to meet. This design shows tremendous promise, and future testing should continue to further validate the time and effort that the ERA team put into this technology. NASA, in cooperation with industry partners, is truly transforming the concept of how we fly. 2025 is right around the corner, and before you know it, many of the concepts the ERA team has studied will undoubtedly be used to make flying safer for all of us.